In the previous video, I had talked about congruent figures. And to prove that two triangles would be congruent, I actually had to show that all 6 parts would be congruent. That would be that all the angles are congruent and all the side lengths are congruent, which is a lot of information. And to get to all that, you really need to be provided with a lot of information. So if you recall that proof, 4 pieces of information were given, and then we only identified 2 of them on our own. Okay, what we're going to start to look at now is how to prove that 2 triangles are congruent without being given a lot of information. How can we prove that 2 triangles are congruent if you only have 3 pieces of information? So we're going to be looking for what we call congruence shortcuts. The first is going to be called the side-side-side congruent shortcut. All right, question. How many different triangles can be made from any 3 segments? How many different triangles can we make from any 3 segments? Okay, so what I'm going to do here is take these 3 pieces of paper, let these represent the sides of a triangle. And what I'm going to do is match them up end to end. I ended up putting these little markings on them just to make sure that I remember what will be the inside in case these aren't actually cut correctly. All right, and what I'm going to do is match up all the vertices. It's a bit tedious here. But I want to be as exact as I can. Okay, that's gonna probably have to work. All right, and then I'm gonna mark off each of the corners here. I'm gonna mark those off. Okay, and then I can connect those to make a triangle. All right, next, what I'm gonna do, I'm gonna call this triangle A. Next, what I'm gonna do is take the same 3 segments and attempt to connect them in a different way. We'll go with this. All right, so again, I got to mark so I remember what was the inside part here. All right, see if I can get them corner to corner. All right, and then we can put little dots, just enough so I can see them. There's one there. All right, go ahead and connect these, and I will call this triangle B. Okay, so my attempt here was to reorganize the sides. All right, what I'm gonna do next is I'm gonna cut these out. All right, I've got the triangles cut out. What I wanna do next is demonstrate that regardless of how I use those segments to build the triangles, I end up actually building the exact same triangle. These 2 are really gonna be congruent, and given any 3 segments, you can only build 1 triangle. All right, so let's take B and attempt to match it with A. Okay, first what I'll do is rotate it. Okay, make sure that obviously the short sides are matching up, and then I'm going to move B on top of A. And you're going to see that doesn't quite match up, right? They're not exactly the same here. We got A sticking up from the back. However, if I take B and I flip it over, if I flip that over, let me see if I can line these up. If I flip it over, I actually get the exact same shape. Right there. In fact, you might not even be able to tell that A is behind it because these are a perfect match. A is back there though. All right, so given any 3 segments, if you're provided 3 segments and you're asked how many different triangles can you make from those segments, the answer is going to be 1. All right, so that leads us to the side-side-side or SSS congruence conjecture. If all 3 sides of one triangle are congruent to all 3 sides of another triangle, the 2 triangles are congruent. We don't need to know anything about the angles. As long as all the sides are congruent from one triangle to the other, the angles will end up being congruent. For example number 1, we're going to prove that 2 triangles are congruent, but we're not going to prove that all 6 of the parts are congruent. What we're going to do is use our new congruent shortcut, which is side-side-side. So to prove that these are congruent, we're just going to show that all 3 sides are congruent. A couple of these are already given to us. KL is congruent to NL. We'll see that here. KM is congruent to NM, which we also see here. All right, so those will be given. All right, and then all we need to do is show a third side is congruent. All right, so we've got our singles. We got our singles here. We've got our doubles right there. The third side for the 2 triangles is actually right here. It's a shared side between the 2 of them. Okay, so that would be the reflexive property. The reflexive property, something is the same as itself. All right, so how do we name it? What you're gonna notice is that on the left side here, I have information that pertains to the left triangle. What I have on the right is gonna be information that pertains to the right triangle. All right, so for the left side here, let's just go ahead and call it LM. All right, so LM is congruent to. All right, in the right side, we have to make sure that it matches up. So it could either be LM or it could be ML. It really just depends on how everything is structured in the individual pictures. All right, so if I look in the first one, point L is gonna be in contact with the single mark side. Point M is gonna be in contact with the double mark side. Okay, so we need that to be the same for the other end here. And you'll notice that L is in contact with the single mark and M is in contact with the double mark. That means that we can write LM is congruent to LM. We don't actually have to switch the letters here. All right, so if we take a look at all the information that we got, the given pieces of information told us that 2 pairs of sides were congruent. We got a couple sides that are congruent. The third part, we proved that the center line being shared is going to be congruent between the 2 triangles. All right, so we've shown that all 3 sides of one triangle are congruent to the 3 sides of the other triangle, which is our congruent shortcut. So we can say that triangle KLM is congruent to triangle NLM by side, side, side. For example 2, we're going to look at the relationship between geometry and construction. It ends up that the triangle is the most stable shape that you can use when building things. The reason for that is the side, side, side congruence conjecture. All right, suppose you were given 3 pieces of wood and asked to build a triangle. Once you assemble that triangle, it can't change shapes. In fact, if you took those pieces apart and attempted to build it again, you'll end up building the exact same triangle that you had. So we get a sense of stability within that triangle once it's built. All right, so we have a picture of a couple of benches here. It might be a little bit difficult to tell, but the bench on the left has a crossbar. The bench on the right does not have a crossbar on it. The bench that does have that crossbar ends up creating a couple of triangles. And those triangles end up being a stable shape. They actually can't change. The bench to the right, because it doesn't have that crossbar, we actually just have a quadrilateral, which ends up being unstable. That bench could actually end up leaning to either the right or the left. But the bench that we have on the left won't. It's going to be completely stable.
Later, blah.